Okay, we'll do a quick rehash of what happened earlier in the week, and from there we're going to shift pretty quickly into the discussion of the assessment task 1. I've been on the forums this morning. The forums are pretty quiet. People are dealing with a lot of stuff in their lives not related to study. And I fully get that, that's fine. So today we're going to try and support you in that by clarifying some of those issues around assessment task 1. You may be already clear, so just sit back and just check your understanding and feel free to share anything you're doing, because some of you are absolutely spot on. So this task really is about scientific thinking, and I really want to get started just by linking it first of all down here to assessment task 1, topics 1, 3, 7, 10, 11 and 15. So as you can see, this week's material is quite generic, and this is one of the things when we're talking about the structure of assessment task 1, how you can go back and connect to as many of our first 5-week topics as you possibly can. And in that material you'll be talking about perspectives, you'll be talking about pedagogy, you'll be talking about a whole range of the different topics we've covered, thinking scientifically, and so really our goal this week is to narrow that down and as we heard from Renee, look at 2 inquiry frames, the 5 E's and the POE, which is a really interesting model, or the POE and E if you're over in the States, Canada, or anywhere in North America, so, and Europe too. But if we have a look at a little cartoon there sort of saying, you know, science is essentially a rational process. Yes, you know, avoid gurus, use science to test theories. And that's really what we're doing. We're talking about thinking scientifically. And as you can see, that range of topics, 1, 3, 7, 10, 11 and 15. So you can see that, you know, this is central to quite a few of the weeks we've covered so far, and the potential topics you may want to look at. So our goal is to explain, describe, outline. I won't talk too much about that, but really by the end of the week, if you can tick those 3 boxes, what is an investigation? Describe 2 approaches to thinking scientifically, and there it is in black and white for you. You know, it's a real tip. These approaches are inquiry-based, and you know, you can actually build, as Renee said, you can build just your strategies for that particular question around either of these approaches or both of these approaches, and just, you know, differentiate between them. And then finally, outline the process of fair testing, which really is at the core of positivist science and empiricism and Karl Popper's old notions of falsification, which popped up in week 2 of the course. So the launching pad this week is, you know, we're all on the same page, essentially. Where do we need to be? We need to understand that investigation is about thinking scientifically, about problem solving, and that problem hopefully is embedded in a real-world context. Predict, observe and explain is one way to actually do science. The 5 E's is another way to do inquiry-based science. And again, it comes out of primary connections and a very popular model here in Australia. And the whole notion of why do we do science? Well, we do science to derive a fair test, a principle that basically says if we control for one variable and we measure the effects of another variable, what does that mean for our understanding of science? So it's a whole notion of a fair test. Now, we can go and argue the whole point, as science does. There's no such thing as a fair test. Philosophy and ethicism actually argues that science is really just a linguistic and constructual framework, but it constantly does its best, as we know from Karl Popper's work, to eliminate against claims of bias and to try to be verifiable, and once it's verifiable, to try to be generalizable to the world at large, so that we're producing scientific outcomes rather than merely whims or notions, or as Donald Trump may, just ideas or ideologies. So the term this week, independent variable, okay, is what I change. The dependent variable is what you measure as a consequence of that particular change. And there's a couple of, you know, really good examples in your smaller textbook, pertaining mostly to chemistry, but there are some good biological ones too. Investigations. We use investigations to engage students. Clearly it's the hook, it's the kinesthetic hook. We provide students with opportunities to learn the skills and processes of investigating, and we provide authentic experience. Now that word comes up time and time again when we start to look at the POE model. Okay, really, it's about authentic experience, and so is the 5 E's essentially, but it, you know, it's borrowed very much on POE, which is a little bit older than 5 E's genealogically, so it actually is an older system of inquiry. And we assist students to develop an understanding of scientific evidence and the nature of science. And we can actually look at that, and really interesting to notice this morning, even as we're talking, that Syria, villages in Syria are currently getting over the most recent chemical bombing. So it's quite a, it's quite an interesting point where science is at this stage. We also have the opportunity to enhance our survival, plan for our futures, or we have the capacity also to undermine that with our behaviours. Hence the value of investigations, hence the power of them. Now POE, a really nice little example taken from Canada and Thames Valley. They do some great stuff in Canada, particularly related to inquiry-based learning. Josh Haysom and Michael Brown, and we're looking at the National Science Teachers Association Press, published this in 2010, and they actually go through and they identify the 8 steps of POE. Your task, clearly, if you're doing this particular question as part of your assessment task, is to, to be able to demonstrate your understanding of these. And for that reason, I've tried to group them into a couple of different stages. Steps 1 to 4 are really about probing your students. Okay, step 5 is about engagement and observation. Step 6 and 7 is about monitoring their understanding. So when you're doing your Peshakusha, you can actually look at breaking this down into 3 different categories here rather than the 8. So we've got steps 1 to 4 can be linked together. Step 5 is probably standalone observation where the student sits and pauses in the world of science. Step 6 and 7, where they then begin to reconstruct their understanding of science based on that notion of what they've just observed. Now, I don't want to go too much into this because I'll be repeating what I said in the lecture on Monday, but step 8 is follow-up. And step 8 is that really, critical stage where the teacher can actually take up and connect the student's experience to the real world. And in that way, it makes it authentic. So steps 1 to 7 usually, and if I go to my next slide, just summarises that for you. Steps 1 to 7 can usually be covered in as short as a 40-minute period. Many teachers, for instance, at the upper primary or the middle primary school level will pause at the end of that observation stage, and we'll just go back and look at that. Okay, there's observation at step 5. Okay, there'll be some discussion towards the end of the lesson where, there is some explanation, providing a scientific explanation so the students can actually start to begin to reconstruct their process, their understanding of science. And at that point, the teacher may set the homework, and the students will go home and write up their results, write up their processes. And so, it's a really interesting point, and that the follow-up can sometimes occur as, 24 to 48 hours later. But essentially, the student in the meantime is constantly doing that reconstruction, constantly sitting in the world of science and dealing with how their observations have been changed, reinforced, enhanced or altered as a result of the POE experience. I actually put up an example for you this week, and the Bricklayers Problem. You can see, it's supposed to be authentic learning. It's a little bit false, but you can see from here clearly how you can have a lot of fun actually in steps 1 to 4 where you're probing students. Well, how can we monitor this? How can we test this? And you can come up with a simple set of gallows, and the gallows can be a simple weighted experience. But notice down here, POE, predict, observe and explain. And unfortunately, science does come down often to worksheets in schools. If you can, take it outside, get students actually doing some of the natural sciences. But when you're testing Newton's law, that's quite a reasonable experiment to conduct, and the students actually get to explain what they think is going to happen. Okay. Now, the Bricklayers problem, as it's known in science, is an ancient one. And we know that once we look at the opposing forces and the weight and monitoring the sand bucket, once we add a little bit of sand to a state of equilibrium, the pulleys are going to shift in the direction of that heavier bucket. So the scientific explanation is quite straightforward to us, but you'd be surprised how many students actually don't get it right. And this was actually conducted at a university level, and year 1 physics class. So we're not talking about science newbies here or naivety. We can see that there are some errors of prediction, even in students at the scientific level that we would think should be able to discern a little bit better than that. And still, when we look at only 90% correction in the predictability of the outcome for such a simple experiment. Now, this is not an argument about how dumb first-year physics students are. This is an argument for the power of POE, for the authentic learning experience, and the fact that, you know, in any given crowd, 9 out of 10 people have a basic comprehension of science, but there's one person out there who really needs to reconstruct their thinking. POE can also go to a role-play situation. And look, we know that the damming of the Mary River was a very popular one down your way, down Mackay, and you know, a lot of role plays built around that in science at the time. We have that up here, for instance, with the development of the gas pipelines, you know, the underground gas. So all of these different issues are coming out where students are actually using the POE framework to look at broad issues. Really broad issues. And, you know, the ABC this morning were debating the impact of mankind on, of course, on climate change and what that means in the future in terms of severe weather events. And so, yeah, we can actually set up a classroom situation where we create roles to reflect different groups, and of course their aim is to research their position and actually bring those together in a conflict situation where science is put to the torch. So you can see the power of POE, you know, even at a collaborative level. And not too many people would think about doing drama in a science class, but there you have it. It's a very productive model. We can also shift on. Now, those of you thinking for strategies, I've had a couple of examples there purely. If you're tackling that question in assessment task 1 where you're looking at 2 different models and 5 strategies, you know, role play, consider it in a science class. It's a little bit out there, but it's certainly under POE lends itself well. POE, sorry, lends itself well to that investigation. Primary science, primary connections, really came about as an inquiry model, and as you can see here, we've got our you know, romantic scientific academics. Tiddles is a cat. You know, all cats have fleas, therefore we should keep him off the sofa. And this is Bertrand Russell's old Christmas turkey argument. You know, it's actually a false argument, and science can take, as Bertrand Russell demonstrated in 1921, science can take a torch to these kinds of arguments, pull them apart, deconstruct them, reconstruct them, and show in fact that they can be falsified and therefore they're not true science. Jean-Francois Lyotard and Jacques Derrida, 2 great deconstructive postmodern thinkers. Lyotard probably wrote around 1930. Jacques Derrida was born 1930, I think. But you can see that, you know, the whole notion of they question whether reason is even an empiric state. So even though science is all about, at the philosophical level, all about proving reason, and Popper has done this, and Bertrand Russell has, you know, written extensively about this, Lyotard actually argues that reason is a fiction. It's like any thought we have, it's really just something we keep thinking and we keep proving. There's no, in other words, in Lyotard's perspective, there's no such thing as scientific reality, or reality of any kind for that matter. Derrida takes it one step further, and he says not only is it, you know, harmful to believe that there is such a thing as reason, but that if we actually believe that, it can lead to self-inflicted harm and suffering. And of course, we are now starting to see the implication of that in our lives, from everything from natural sciences, the weather, population degradation. We're starting to see just how far some of these arguments and how far-reaching they are. And again, they make great material for a 5Es classroom. Now, my aim here is not to repeat what I set out to talk about in the previous lecture earlier in the week, but you should be familiar with the 5Es. It's in the course material, and it's, you know, it's quite explicitly set down there. But the reason why I've actually carved this up and served it to you in the PowerPoint slideshow is the 5Es are explicitly stated: engage, explore, explain, elaborate, and evaluate. And by the way, over in North America, POE is, you know, predict, observe, explain, and evaluate. So it goes often POE and E. So evaluation is being added on to that model. to make it explicit. I mean, it was always there, but just to make it explicit. But you can see the purpose is listed there. And, you know, again, this is very useful to you in your assessment task 1. So you'll be looking for, in your narration of your Peshakusha, you'll be talking about a slide, you'll be talking about creating interest, and then you'll be presenting images of activities in a multimodal domain. You're looking at students getting excited about their science. There'll be questioning, there'll be inquiry, there'll be a whole lot of activity around learning. Learning will look a certain way. And your whole task with this Peshakusha is to, you know, deconstruct it, to deconstruct what the 5 E's may look like, and to come up with the strategies. Okay, engage by creating interest, by questioning, by establishing meaningful and authentic content. There's a lot of connections here between POE and 5 E's, and that's why I suggest do one or the other, don't do both. Okay, try and differentiate it against a different model of teaching science. So you can see there, those strategies are quite explicit for you. Engage, there's 3 clear strategies there for engagement. As you can see, there's 2 clear elaborations on what it means to explore. There are 5 elaborations there on what it means to explain. There are 2 elaborations on how to evaluate, and there are 3 elaborations on how to elaborate. So, you know, these are the strategies that you will try to bring up and try to speak to in your Peshakusha. So please, you know, have a close look at the 5 E's. It is a model that lends itself well to many of the questions. Thinking scientifically, why is science important in the lives of people? Question 1, you know, all of these topics are definitely related. And the 5 E's can be a very strong strategy for applying your understanding and demonstrating it. Activity 2 this week, you had to choose a strand. And here's just a little example of what that was like. This is the kind of, you know, evidentiary base. When you get into your Peshakusha, you need to really step your audience through it. Now, assume it's a presentation. Assume you have a real live audience in front of you. And, you know, even though it's tricky reading onto a PowerPoint slide, you know, it's very hard to not be robotic about that. If you can, try not to be robotic. Try to be excited. Try to put emphasis in the places where emphasis needs to be put. So it's really important here. You pick your strand. One I sort of used here was learning Aboriginal and Torres Strait Islander concepts of time and weather. And of course the connections of that to the dream time. Linda came up with one of her own from last year, where she looked at biological sciences. The descriptor was living things, non-living, once living. So a broad range of things there. It's a really good one to choose, and I liked that choice. And for instance, discuss how you would engage students before you start this unit of work. For instance, you may bring in different objects, living and not, and working towards a definition of what construes them as living or not living. You may look at baking something or eating food, where it comes from. Was it once living? And again, the point I make in the lecture is, you know, there's a very high percentage of primary aged children who have no idea, for instance, where steak comes from. They think sausages grows on a tree. There was an April Fool joke a few years ago where someone went to an old vineyard in South Australia and put spaghetti all over the vineyard. And on news that night, of course, was the blossoming of the spaghetti harvest for the year. And of course, that created such a discussion point on April 2nd in schools around Australia. Many of the students watched it and were talking about the spaghetti trees. So it really is important, even though this may seem very simple. You know, these kinds of concepts are quite strong, and it links us back to our fair testing. You know, the example given for this week was plants, you know, torturing one poor plant by administering salt water to it. So that's the independent variable, the different levels of salt. The objective measures we have will be the height of the plant. What are we looking at? Okay, what are our metrics? We've got the same plant, the same amount of water, the same amount of soil, the same amount of sunlight. Okay, our narrative there comes, and again we're talking about week 3 here, the narratives. What happens to the height of a plant, the dependent variable, when we change the amount of salt added, the independent variable? How can we describe the effect, that is the data measures, perhaps in terms of centimetres, condition of the plants, the presence of parasites, the immune compromised state of the plant as a result of consuming salt water? There are a whole range of ways that we can actually measure how the plants are doing. So a little example, a very simple example of what we mean by a fair test. Now, please, I'll pause there and ask if anyone's got any questions at this stage. That year level example from Lauren, I believe that one is a year 3 example too, the one from the amount of salt.
Hi, Colin. I've got a question.
Yes, Julie.
So I've chosen the engagement in science education for my presentation. With the 5 E's, is it okay for me to mainly focus on the engage and explore because that's most relevant to my topic, or do I need to be talking about the others as well?
No, definitely. I mean, when you break down, you've got 20 slides, so obviously you're going to be talking about the importance of engagement. You're probably going to want to be introducing the model, Julia. And
yeah, I've already got about 10 slides so far.
Fantastic.
And now I'm just about starting the actual, like where I'm giving examples of activities that I would do in a classroom. But I just want to know if I need to be looking at the other steps of the 5 E's, or if I can just focus on those two.
Look, I think definitely put the emphasis on those two, where you're looking at engagement and you're actually exploring and building up a theoretical framework around engagement or frameworks. But when you get to the end of your presentation, make sure you connect that back, that you close the circle and you bring it back to your topic, say engagement, properly done, properly executed and, properly emphasized and embedded is actually going to lead to a better inquiry process.
Okay.
So engagement is an opportunity for you to demonstrate your understanding of a broader framework here and its importance. Okay. Yeah.
No worries. And also, one of my slides is only 16 seconds of sound. Obviously, I can't say much more in like 4 seconds. Is that fine?
That is absolutely fine. Yeah. Yeah. And you may want to compensate for that by just freezing an image, putting what you think is a powerful image there so that the audience can just sit there and wait for the slide to tick over and not probably even notice that, Julia.
Okay, thank you.
Yeah. I'll be on the lookout for it now, though. Thanks for your questions. Excellent questions. Anyone else from the floor?
Colin, can I just ask also, with that curriculum example that you've got up there in the top left, where is that from? What year level is that one from?
Top left?
Yeah.
That's just the elaborations document. Okay. It's come from the ACS elaborations, and it's in, I think it's the environment strand.
Okay.
Yeah, and all I've done is just basically just cut the elaboration to show that within there's 3 different elaborations you could choose within the one content area. And the one that I was going to elaborate on there, I didn't do it because it's really, just demonstrating the 3 different things even under the one elaboration. You can actually go in 3 different pathways. And the reason I do that is to demonstrate that when you're looking at these areas, here's a cue to you where you can find some images.
Okay.
Where you can actually look and see how these elaborations can actually stimulate some images for you that you may be able to include in your Paishakusha and actually use for purposes of discussion and narration.
All right. Thank you.
You're welcome. All right, moving on. I finished the session last Monday with some scientific possibilities in your classroom, and the aim is to come up with this whole notion of a fair test, balanced and unbalanced forces. So Newton's first and second laws of motion. Again, I've used robotics extensively to explore those. And for instance, I remember with a group of Year 9 kids I actually took as part of when I was working at JCU. They were a real challenging group, and the school really didn't know what to do with them. So we built a project around them, and where we actually rebuilt a Harley-Davidson motorcycle, and we also used a lot of robotics and hands-on stuff in their education. And I remember we built an automated robotic toilet cleaner using Lego robotics, and when people came into the classroom it was quite a shock, because in the middle of the classroom on a table was a porcelain toilet bowl. And all around them were young boys of Year 9 level, as you know what they're like, and basically working on solving this prickly task of who could build the fastest, neatest, cleanest automated toilet bowl cleaner. And of course, their understanding, their situated understanding and their numeracy and literacy around the first and second laws of motion were just profound. The way they actually built robots that could cling to a toilet upside down and actually clean under the rim, you know, is really quite impressive. At the primary level, the early childhood level, towing a trailer with a group of early childhood kids and Lego robotics. A simple rope, a tug of war, Newton's third law of motion, action and reactive forces. Galileo's famous experiment on the moon, we had a discussion on that a few weeks ago. He proposed in the 1600s that a feather and a coin would drop at the same rate on the moon. And of course, one of the first things Neil Armstrong did when he landed on the moon was repeat Galileo's experiment. And Galileo actually was correct. So the feather and coin mystery, gravitational attraction and air resistance. So really simple things. Why does the feather fall more slowly? And reducing friction. Now, we might think, how do we do that in a classroom? Well, all you really need is a force meter and a couple of books of different sizes. And all you do is pull the book. You put the book on its edge, on its thin edge, and you pull it. And you measure the force. You put it on its flat edge. And then you say to the students, why? Let's repeat that. Let's try different objects. Let's have a bit of fun with this. Let's do it with your lunch. Okay, what force meter is it? You know, is embraced there in your sandwiches. Some really, really strong scientific explanations, and you can see the engagement value there. Yeah, which is really important. People doing engagement too, as your topic. Do have a look at some of the examples that Linda's put up. There's a very good one there on engagement, and it gives you some idea of how a student, you know, prior to you has actually tackled the problem. And then, of course, set your bar slightly higher. The topics. Now, I've just carved a couple of topics out of the question sheet. The world is complex, never changing. Okay, yep. We don't need to question that. But you could come up, for instance, in your first slide, you could come up with some images of that, some examples of that. Present a researched argument as to why citizens should have good scientific knowledge about science, and that goes all the way back to week 1. Different learning theories and theorists, behaviourism, cognitivism, humanism, constructivism, for example. Some of those are quite old. If you can, try and bring it forward in time if you're going to do that one. Choose one and explain how it aligns with your view of teaching. So the important thing is there, choose one. Now, if you're looking at constructivism, for instance, you're talking Vygotsky. If you're talking Vygotsky, you could bring that forward into the 21st century. You could be talking about people like Siemens. You could be talking about people like Mitch Resnick, Randall Pinkett. There are a whole range of contemporary researchers who use constructivism.
Sorry.
Yes.
Constructivism, does that link quite closely to an inquiry-based?
It absolutely does. And think about it, Lev Vygotsky published his theory in 1921, but because he was in Russia and he was essentially Western, Russia had just been through the Imperial Revolution and they put to death in 1917 their monarchy and the royal family. So Russia was in turmoil, and Vygotsky came up with his great theories in 21. Unfortunately, they never really reached the public till 1960. And he talks about the zone of proximal development, ZPD. And that's the reason why I raise that. And ZPD really is that interaction, is that zone where students and teachers come together in an inquiry model. Make sense?
Yeah, thank you.
You're welcome. One of the 3 cross-curriculum priorities in Australian science is Aboriginal and Torres Strait Islander histories and cultures. A lot of people enjoy that topic. A lot of people enjoy and are motivated to look at cross-cultural models of science. It's a really, really good one. It's week 4, essentially, all over again. And there's a lot in there for you to deal with and explicate. It's a good one. Inquiry approach, such as the 5 E's, such as the other 8-step one we're looking at the moment. Observation, predict and explain. POE, predict, observe and explain. Include an example of how it could be used for a particular topic. So you're only going to use one for question 7, and you'll be going very deeply into that and how it could be used for a particular topic. So if you're using the 5 E's, okay, you may want to take those 20 strategies and demonstrate how they can be applied using the 5 E's and come up with a scenario as to what that may mean for learners and the outcomes that you would assume students would have at the end of being through that inquiry process. If you're doing POE, same thing. You know, there's 8 steps involved. POE kind of lends itself more to older primary school students. So think about your audience, think about your learner, and in the early part of your presentation, justify. You're in complete charge, there's no right and wrong, but justify which model you're going to use and justify your application of it because. Question 14, the historical origins of scientific knowledge includes both Aboriginal and Western examples. Again, very similar to question 4. Okay, yeah, I won't say too much about that, but it's focusing more on the history of science on that one. And again, bringing that forward into what we might call the narrative or the storytelling framework. Remember, it's week 2 we spent some time, week 3 also, and in week 4 we revisited the notion of the story or the narrative mode of teaching science. Question 14 is essentially about that. Question 15, outline the importance of connecting children's scientific knowledge to the real world and the way scientists work. So here we go, this is the big one, very similar to question 1 if you really look at them. How can you make science learning authentic and make connections to the scientific community? Well, POE, really it's sitting there, isn't it? And perhaps even the 5 E's. So as you can see, these questions, once you unpack them, you can see that really, oh gosh, I could do so much here. You know, I could actually have a huge choice of where I wanted to put my effort. The challenge for you though is to where to put the emphasis in your presentation. The topics are quite similar. They do require you to give a broad coverage, but you know the emphasis is the key thing, and that's why I'll offer this just to help you get going. So when you're designing your PESHA, or even if you've done it and you just want to check what you've done, at the centre of it all, of course, is a product of 20 by 20. You're going to have the APA referencing system attached at the end of that, so you may have 22 slides. It's all right. Don't worry, the assessment only counts the 2020. So in slide number 1, you're going to justify your topic. I mean, they're all great topics, but particularly you've picked one for a particular reason. Why? Allow yourself 2 slides to give that topic context. So when you think about that, that's 40 seconds. You've got to break down the topic and signpost, a really important part. Signpost where you're taking the audience, you know. We are going to look at engagement. Engagement, why? Because it's the core of the 5 E's model. It's where the POE model starts, and it also is where real-world science starts. So take a signpost where you're going to take your audience. That way, I can come along with you and just say, yeah, wow, you told me you're going there. Yeah, you told me you were going there. Wow, I'm really enjoying this. This is better than Netflix. Okay, so it's really important to signpost. Allow yourself about 2 slides to do that. Then make your connection to its place in science education. Now, we've covered 5 topics. Okay, now it's week 5. This week it's thinking scientifically. So you're going to have more than one area where you can link your topic to. It may not be all 5, but certainly your topic should link to more than one area. So in 2 to 3 slides, you should be able to make some really strong connections to the ACS strands, substrands and elaborations. This is important because, okay, this is evidenced here in the work that we've done. Step number 3, 3 to 4 slides. Your theoretical and pedagogical underpinning. So what are the theories? Cognitivism, behaviourism, constructivism. What are the pedagogical underpinnings of each? You may need to put more than 3 to 4 slides in there, okay, depending on your topic. This is just a rough guide, but the aim is to make explicit the relevant theoretical perspectives and the pedagogical imperatives or the pedagogical emphasis. Now, often it's around inquiry, it's around engagement, it's around POE, it's around cultural perspectives or minority perspectives. So these are the areas where you're going to be exploring those theoretical and pedagogical underpinnings. Making sense? Or does someone have a question they'd like to ask after stages 1, 2 and 3? All right, I'll continue. Stage 4, classroom applications. So once you've actually laid down the foundations, your topic, you've talked about its connection to our course so far. Okay, it's embedded in the role of a science teacher. It's embedded in the learning of science. It's embedded in thinking about science. It's embedded in curriculum models and design. It's also embedded in pedagogical strategies. So slide number 2 talks about those 5 things. Slide number 3, your theoretical and pedagogical underpinning, where you start to unpack it. You start to talk about who the theorists are, why it's important, what the pedagogy is, what it looks like, smells like, tastes like. Then you move to step number 4, where you've shifted from laying the ground to actually now looking at the application. You've gone from theory to application. So how does this theory manifest? How does, for instance, engagement look in a science classroom? What is the teacher doing? Let's go for a balanced perspective. Slides number 5, or point number 5, 3 slides. How does this theory manifest look in a science classroom? What is the learner doing? Break it down. If I'm engaged in constructivist teaching, what does the teacher do? What does the learner do? Come up with some images, come up with some justifications, link it to your curriculum, link it to your strategies and your pedagogy. And finally, we're starting to close the circle. Okay, you can't head off into outer space, even though this is space, earth and biological science. We want you to come back to earth, back to your topic. So when you're closing the circle here, what does your analysis say about your topic? Can you connect to each of week 1 to 5? And so in other words, have we looked at the scientific perspectives? Have we looked at teaching scientifically? Have we looked at pedagogy? Have we looked at culture? You know, in other words, close the circle. And at the end, your patient crucial should really be a nice, concise statement of where your topic starts and where you're bringing the topic back to. Now, you have control over this. I'll say straight away, there's no right and no wrong. It's just about how you do it. Everybody dances. Some people look really cool and other people don't look so cool. So the aim is to look really cool in your handling of this topic. You're in total control. You pick your own topic. You break it down. You link it. You make it explicit to perspectives. You then talk about how it looks from a teacher's perspective, how it looks from a student's perspective or a learner's perspective, and then you bring it back and say, therefore, in 5 slides, this is how science explodes in the mind of young people. Questions, anyone? Comments? Feedback? It's a lot to take on board. How does it check with what you're doing yourself? Is it consistent with what you're doing? Thanks, Fiona. Yes, I'm glad the slide does help, because it's a very loose concept, isn't it? 20 by 20, I mean, where do you start? It's a little bit like writing a small novel. Any other comments? Thank you. That's great to know. All right. If there's no other comments, the thing I need to do then is actually to get this downloaded from Zoom and up onto a YouTube for you, so that you can go back over it and have a look at how this checks. The understanding I'm presenting here, how it checks with your own. If there's any gaps, please don't hesitate to make contact. Okay, put it on the Q&A or just shoot me an email and say, I'm doing something different and now I'm worried. Don't worry. My essential message is that you're in control. But if you're not sure where to start, or you're not sure on the right path, here is, a 60-40 model. If you're following this,